Hello students, today we will be discussing two topics. The first one is the interrupt vector table, which is a very important topic in relation to 8086 interrupts. And the second topic is the various steps involved in interrupt servicing. So let's begin. Starting with the definition, let's go word by word. Table means a list of entries and vector with respect to interrupt means address. Try recalling the concept of vectored interrupts which we have discussed in the previous video. So we can write an interrupt vector address or IVT is a structured list containing the addresses of interrupt service routine or ISR for various interrupts. So IVT is a structured list containing the addresses of interrupt service routine, that is ISR, for various interrupts. Now in some text you can also notice the concept of interrupt pointer table. I would like to mention here that interrupt pointer table is no different from interrupt vector table. Both the things means the same. So interrupt pointer table, or I can write IPT, is same as that of your interrupt vector table. So both of them are synonyms of each other. In some text it is mentioned as interrupt pointer table, and in some cases it is mentioned as interrupt vector table. So both the things mean same. Please do not get confused with respect to the terminology mentioned. From now onwards I'll be referring to interrupt vector table. So with this definition in mind, let us move forward and get into the details of what is an interrupt vector table with respect to 8086. From our previous discussion, we know that the interrupts can be executed by means of int n instruction, where n refers to type number, and this value varies from 0 to 255. So we are having 256 interrupts in total. Software interrupts. The interrupt vector table should have the addresses of the various ISRs for these 256 interrupts. Now what do we understand by the term addresses of the ISR in this case? We know that in 8086 the physical address of any instruction is determined by code segment and instruction pointer. So physical address is determined by code segment and instruction pointer. So by now I think you should know what is the formula for calculating the physical address if the code segment and instruction pointer value is given to you. So code segment into 10h, and it will be added to the value of your instruction pointer. So this is the way of determining your physical address. Now this physical address will be of 20 bits in size, but to get this 20-bit physical address, because the address line is 20 bits, so to get this 20-bit physical address you need code segment value and instruction pointer value, which are of 2 bytes each. So code segment is 2 bytes and instruction pointer is also 2 bytes. To determine the addresses of an ISR, we need CS and IP value. Now there are 256 interrupts, so there will be 256 unique ISR addresses. So 256 unique ISR addresses, which we have already mentioned here. So if we try to calculate the total size of the interrupt vector table, we can write 256, that is the number of interrupts. Each address for an ISR will be having 4 bytes in size because it contains the value of CS and IP. So this will be 256 into 4. This gives you 1024 bytes, which I can also write as 1 kilobyte. Now that is the reason why your interrupt vector table size is 1 KB. This 1 KB we have also discussed in the very first video, that the interrupt vector table size is 1 KB. So this is the reason, because 256 interrupts, each interrupt needs an ISR, and each ISR will have an address which consists of code segment and instruction pointer, which is provided by 2 bytes each. So therefore 4 bytes, which will result in final of 1 KB of space. Now the interrupt vector table size is allocated in the starting part of the memory. So this 1 KB is located in the starting part of memory. The address range will be your code segment and IP value will be 0000 two code segment will remain the same, and the final values will be 03FFH. Now how this 03FFH, this we have also discussed in the very first video. Please refer that video. For time being, I can just say that 10 bits will be used because it is 1 KB. So 10 bits will be used to generate the final address, which will be all be ones. So that is why you are getting 03FFH. Now let us look at the memory map to gain more clarity about the interrupt vector table. Now here we are trying to represent an interrupt vector table. Let me first explain you the format here. So this column, if you see, it contains the various code segment and instruction pointer address, which has been separated by a colon. So here the code segment is 000, that is 4 zeros, followed by IP, which is also 0 because it is the starting memory location. And thereafter, if you see that this is the entire code segment, where the code segment remains same and the instruction pointer values gets incremented for every memory location. We have also discussed many a number of times that every memory location, the basic memory unit size is 1 byte. So using this CS and IP address, you are getting a physical address which is 5 zeros, and this memory location holds only 1 byte of data. So 1 byte size data is stored in this memory location. Likewise, all the memory location stores here 1 byte size. If you see various physical address, they are generated by the same formula, code segment into 10H plus your IP. So here, suppose if you look at this address, the code segment is 0, then it will be multiplied by 10, which will result in 5 zeros, followed by adding with 3 zeros A. So you get the final address of 40A. So this is your physical address. Now we have understood that for any interrupt to be pointed to an ISR, we need 4 bytes. So for the first interrupt, or your, let me write it here, type number is from 0 to 255. Now if I want to say that type 0 interrupt has to be executed, so in the previous video we have seen the type 0 interrupt is also called as divide by 0 interrupt. So if the type 0 or divide by 0 interrupt has to be executed, this needs to go to that specific ISR. So here the first value will be the instruction pointer lower byte for type 0. Okay, so let me expand this, and the second memory location will be instruction pointer, but this will be your upper byte, or I can write higher byte. So likewise, the next two memory location will be your code segment data. So I can just copy paste this, and sorry, it will be here. So this will be your code segment lower byte for type 0, and this will be your code segment higher byte for type 0. So this is how the remaining memory locations will be there. So if you see for type 1, like if I write here, for type 1, that is your single step interrupt, if I want to get the ISR address, I will have to go to the next set of memory location, which will start from 4, 5, 6 and 7. So 4, 5 will contain the IP lower part, which I am writing as IPL for type 1, and the next memory location will contain IPH, that is the IP higher byte for type 1. Then it will be CS lower byte for type 1, and the next memory location will have CSH for type 1. Likewise, the remaining memory locations will also be arranged in the similar manner. Now what we need to understand here is the first memory location, or the first part, will be your instruction pointer, and the second set will be your code segment. We have also known that the higher memory contains the higher byte and the lower memory contains the lower byte. So if you see the code segment 002 and 003, these two are the memory locations. So the lower memory location is 2 and the higher memory location is 3. So that is why the lower byte of the code segment is present at the memory address 402, and the higher byte of the code segment is present at the higher memory address 403. Likewise, your instruction pointer, the lower byte will be at the lower memory address and the higher byte will be at the higher memory address. The same pattern will be followed here. So if I want to write in the last address, that is your 003FFH, so here I can write this will contain the code segment, the higher part for type 255 interrupt, and this will contain the code segment lower part for type 255. Then if we move on up, we'll be getting the instruction pointer, the higher byte for type 255, and this will contain instruction pointer lower part for type 255, and above that will be 254 and so on. Based on this concept, let us try to formulate what will be the general formula in order to determine for which type number we need to go to which physical address for obtaining the instruction pointer and the code segment for that respective interrupt service routine or ISR. If you had observed the pattern followed here, you would have been able to see that for each type there are 4 bytes allocated. So we can easily calculate the final physical address for your instruction pointer as well as your code segment. So I can write instruction pointer for the ISR of type n is given by a general formula as 4n, where n is your type number and the code segment for the ISR of type n interrupt is given by 4n plus 2, where again n is your type number. So let us try to take an example and get it. Suppose for type 1 we want to get what is the instruction pointer value and what is the code segment value. For type 1 we can write the IP value will be 4 into 1. Here n is 1, so that is I 4 into 1, which will provide you 4 zeros followed by 4h, and your code segment value will be 4 into 1 plus 2, which will give you 4 zeros followed by 6h. Since instruction pointer is of 2 bytes, it will automatically include both 4 and 5. Likewise, your code segment starting memory location is 6, so it will automatically include 6 and 7h. So this is the general formula for getting your instruction pointer of the ISR of type n, that is your 4n, and code segment value for the ISR of type n interrupt, where n is your type number. It is given by 4n plus 2. So these two are very important formula. Let us try to understand by means of some examples. Suppose we have got a question which states, determine the physical address of the ISR for the given interrupt vector table. So the interrupt vector table is provided here. If type 0 interrupt is encountered by 8086 microprocessor. So let us get clear with the question. So interrupt vector table is provided here. So with your CSIP values and the physical address and the corresponding data which is stored at that physical address, and it is said that the type 0 interrupt has been encountered. So which physical address the microprocessor should go for executing its ISR. Now we know that the instruction pointer value for any interrupt, the ISR will be located at 4n. So 4n, let me write n in capital. So 4n, where n corresponds to the type number. In this case, the type number is type 0. Type 0, here the type number, that is n, equals to 0. Now please understand, this type number usually you will get in the format which is decimal. So the type number is always expressed in decimal, but you have to convert the final physical address in hexadecimal format. So let me take this case first. So here instruction pointer equals to 4n. So if I do 4 into 0 will be 0. So this will be 50h. And what about your code segment? So code segment equals to 4n plus 2 equals to 000 to h. Let us see what is the data stored at this address and this address. The instruction pointer will be stored at this address. Please understand, this is not the value of the instruction pointer. It is the value at which the instruction pointer of that ISR will be located. Here at this address, that is your 50s, you are getting these two values. Okay, so 3405. So the actual value of your instruction pointer. So this is your address of the ISR IPs. I can write instruction pointer, and here it is the address of the ISR code segment. Final IP of the ISR will be 3405H. because the higher byte one is located at the higher memory location and the lower byte is located at the lower memory location. So that corresponds to 3405H. Then we are having the code segment of the ISR. So this value will be 200H. So we can write 2 followed by 3 zeros H. This is the final IP and CS value of your ISR. But we should not stop at this point yet. We have to determine the physical address as it has been asked in the question. So the physical address is obtained by port segment into 10H plus your IP, which corresponds to 2000 will become 20,000, and 20,000 if added with 3405, it will be 23405H. So if a microprocessor is already executing a task and divide by zero interrupt has been encountered, what the microprocessor will do? It will pause that program, it will transfer the required contents onto the stack. Now what are the required contents? We'll understand it later. And then it will start executing the ISR for divide by zero interrupt, that is your type 0 interrupt. To go to that ISR, it has to calculate at which location will be your instruction pointer and code segment. So that is calculated by this method, that is 4n and 4n plus 2. Once it gets to know at these two addresses the address of the ISR is located, so it will fetch from this two memory locations your IP and these two memory locations your CS, calculate the physical address. So it will go to 23405. So I have made it in the interrupt vector table to that location. So it will come to this location, that is 23405, which is pointed by 2000 CS and 3405 as IP. So here some instruction code I have written, some random code, move AX, BX, which will not be stored as move AX, BX, but in the hex code format. So this is the flow. Now what I want to state one more point here is, in this case it is quite simple. So here we have got type 0. Now suppose the question would have been, determine the physical address of the ISR for the given IVT if the type, let me write here, 255 interrupt is encountered by 8086 microprocessor. What things have to change here? Let me make some changes first. So here n is equals to 255 and you are having a type 255 interrupt. So accordingly, your instruction pointer as per the formula 4n will not point to 000H. Instead 4 into 255 will result into 1020. Now this will not be hexadecimal value. So this will be 1020D. And similarly this CS equals to 4n plus 2. This will also be 1020 plus 2 will give you 1022D. But we need the address in hexadecimal format. So again I am repeating, whatever the type number you are getting is in decimal format, that is 255 is in decimal, it's not in hexadecimal. When you multiply this by 4, you will be getting a decimal value. In the previous case, 0 in decimal and 0 in hexadecimal was same, that's why I have directly written as 50H. But in this case, this is 1020D. So you can convert this into hexadecimal. So let me open my calculator here. If you see here, I am punching in 1020. This corresponds to 3FC. So this I need to represent 3FC in terms of 20 bits. So this will be 003FCH. And if you add plus 2 to 3FCH, will become 003FEH. So this is your final code segment address. Now as you can see, this point, that is your 3FC and 3FD, this holds the IP value for your type 255 interrupt. So let me take this value as 22 and this value as 33, this value as 00 and this value as 40. So what will be the IP of the ISR? So we can write here, all these values are in hexadecimal. So let me write here, this is 22H, 33H, 00H and 40H. So I can write the instruction pointer value is 3322H because the higher byte which is stored at the higher memory location, that is 3FD, and the lower byte which is stored at the lower memory location, 3FC. So 3322H, and the code segment value is 4000H. So what will be the physical address? The physical address, you multiply the code segment into 10, so it will become 40,000. So the final physical address has to be generated by both CS and IP. So you'll be getting 43322H. At this physical address will be your ISR for your type 255 interrupt. I'm summarizing the entire thing for similar type of questions. If you get, first you have to see what is the type number of the interrupt. Now the interrupt is type number is always given in the decimal format. So here if it is given as the type number is 220, so it will be 4 into 220, which will give you 880. Now 880 has to be converted into hexadecimal. Likewise for your CS, again you have to add +2, convert that into hexadecimal, and that will be your final physical address at which the IP and the CS of your ISR will be stored. Obtain the values from of the IP and the CS of the ISR individually, then you form the physical address for that ISR. So this is the sequence of steps which you need to follow to determine the address of the ISR if any type of interrupt is given to you. Now we are done with this. Let us move to the next part. Moving to the next part, which involves knowing about how the entire interrupt vector table is divided into. We are aware that we have 256 interrupts, and these are further categorized into various types. So let us get into the details. Now the first 5 interrupts which you have seen in the previous video are called as predefined interrupts, also known as dedicated interrupts. These interrupts are 5 in number, which varies from type 0 to type 4. They are also called as predefined interrupts. So we have seen in the previous video, type 0 was called as divide by 0, type 1 as single step interrupt, type 2 as NMI, type 3 as breakpoint interrupt, and type 4 as overflow interrupt. So these are dedicated to specific functions and which are predefined, but the ISR or the interrupt service routine for those interrupts have not yet been written. It has to be written by the programmer or the user. Now the next set of interrupts, they are called as reserved interrupts. They are 27 in number, so their values varies from type 5 to type 31. So if I want to write here, let me first write for the this value varies from type 0 to type 4, whereas for the reserved interrupts they are 27, so type 5 to type 31. Now these reserved interrupts are reserved for Intel, reserved by Intel for use in its future level of processors. Now what does this mean? As we have discussed before, the 8086 microprocessor works as a base for development of the various x86 architecture of your microprocessor, and that is why these interrupts type 5 to type 31 are reserved for the future level of processors which were developed later point of time. Now coming to the third type, these interrupts are called as available interrupts, and they are the remaining ones. So 27 plus 5 is 32. If you subtract that from 256, so you'll be getting a value of 224. So they are 224 in number, and this value varies from type 32 to type 255. These interrupts, they are available to the user to be used as hardware or software interrupts. Here the user can define it specific interrupts for hardware or software. So for example, suppose INT39. Now INT39, this can be defined as a hardware interrupt. So suppose one device which is connected to the INTR pin. So if I am saying that this is connected to an INTR pin, which is a printer. So if a printer wants to be allocated an interrupt or interrupt service routine, so it can be assigned INT39. Now this INT39, whenever the printer wants to send a data or receive a data, it will send an interrupt on this type number, that is INT39. The microprocessor will receive INT39 and it has to generate the interrupt acknowledge cycle. Please remember, we have discussed this, how the peripheral device generates the interrupt acknowledge cycle, and it sends its type number, that is 39, to the microprocessor. So 39 is converted into hexadecimal, so you can convert 39 into hexadecimal, and that is sent on the lower byte or the lower data lines of your microprocessor. So that is sent to the microprocessor. 39 in hexadecimal is 27H. So 27H is sent to the microprocessor. The microprocessor, with respect to 27H, it will calculate where the ISR is depending upon the physical address which is generated using the formula 4n and 4n plus 2 for the IP and CS. Once the IP and CS values are obtained from those values, it generates the final physical address and goes to the ISR to execute the interrupt service routine of the printer. So this available interrupts are for the various hardware and software interrupt, and it is available to the user for its purpose. Now it may be noted that whether it is an external or internal interrupt, so whether it is a software interrupt or whether it is a hardware interrupt, it is assigned with a type number. That is the conclusion which I want to point it here. So whether it is an external, so external here means hardware interrupt, or internal, so internal means software. Now software can be with respect to your INTN, or it can also refer to the specific condition. So please remember, in the very first video we have discussed the various sources by which an interrupt is generated. One was your external or the hardware, one was by means of software, and the third was by some specific condition. So the internal includes the last two aspects, that is your software or by means of specific conditions such as your divide by 0. Now whether it is an internal or external interrupt are mapped to your type number n, and once we get the value of n, the corresponding ISR addresses are generated using the formula 4n and 4n plus 2. Now let's have a look at the entire interrupt vector table when we incorporate all the three different categories of the interrupts. So you can see here, at this point we are having the dedicated interrupts which are 5 in number. So here you are having 002, 003. So the starting memory location is 004 for the type 1 interrupt, and type 2 interrupt starts with 008. So all these values which are presented on the left hand side is the starting addresses of the interrupts. Here in the memory map which I have shown to you, one memory location which was containing 1 byte, but here they have shown 16 bytes at one stretch. Here this is your IP address, that is IP offset, and this is your code segment base address, that is first your IP address or IP value is stored and then your code segment value is stored. Likewise you are having for the various interrupts. So the first category, that is the 5 interrupts, type 0, type 1, type 2, type 3, type 4, we are having your dedicated interrupts. Now we are going to the reserved interrupts which are 27 in number, starting address of 14H. So this starts with your type 5 which is a reserved interrupt, and this will carry on till your type 31, and thereafter you are having your available interrupt pointers, so which are 24 in number, and that the first one, that is your type 32, will be having a starting address of 080H, and thereafter the final one will be having the starting address of 03FCH, which we have already seen, and the interrupt vector table will get terminated at the location 003FFH. This is how your interrupt vector table looks like, the entire stretch, and this is also what will be expected for you people to draw when asked in the exam. You need not to mug up the entire thing, you can just remember the addresses. So if you know type 0, you can calculate by using your calculator what will be the starting address. You can write down the addresses here and write type 0, type 1, type 2, type 3, type 4, which are your dedicated interrupts, 5 in number. Then you can write the starting address of your reserved interrupt pointers, type 5. So 5 into 4 will give you 20, which is 014H in your hexadecimal. So this 014 will be pointing to your type 5 pointer, and thereafter you will be having for your available interrupt pointers. So the starting address will be 080 and the final address will be 03FF, or you can calculate the starting and the final address for each section, that is your reserved interrupt pointers. So starting address is 00014H and the final address will be 0007FH, and likewise for your available interrupt pointers it will be 00080H and final will be 003FFH. So this you can easily calculate using your calculator if you know the type numbers. So with this we are done with your interrupt vector table or interrupt pointer table. Now we'll be going to the last leg of your 8086 interrupts, that is how an interrupt is serviced or what are the various steps involved in the servicing of an interrupt. In this topic, that is, what are the steps involved in servicing an interrupt, the concept of stack and stack pointer plays a very important role. The steps which are involved in servicing an interrupt is very much similar to the functioning of your call instruction. When we are discussing call instructions while covering the topic 8086 interrupts, I have explained using memory map. So please refer to that video. So I'll not be going into the memory map with this perspective because it would be very lengthy. So I'll just list out the process. Now from the exam point of view, you can write in words or you can also write in notations. So it depends upon you. What I will do here is I will write in a notational format. And since if you have understood the notational format, you can also express the same thing in words also. We know that the stack pointer points to the top of the stack. So already at the top of the stack there will be some data there. So if a microprocessor is running a program and it is executing an instruction and it gets interrupted by an interrupt, you get an hardware interrupt or software interrupt, so whatever be the interrupt, the microprocessor is interrupted in between. Now it needs to stop its work there depending upon the priority, or whether it is a non-maskable interrupt or if it is a maskable interrupt, and your interrupt flags are accordingly set. So what the microprocessor will do is it will stop at that point and it will go to the interrupt service routine for that interrupt. But in between that, it also needs to ensure that once the microprocessor has executed the interrupt service routine of that interrupt, it will come back from where it has left. Alright, so now where will it store all the data corresponding to the program which it was executing before it encountered the interrupt? The answer is stack. So, and what are the data which needs to get stored? The most important point is we have to store the physical address of the instruction which has to be executed next is determined by two values, which is your IP and CS. So these two values will go to the stack. Apart from that, the flag register which determines the status of the microprocessor, that will also go to the stack. So flags will also move to the stack. So this is the basic idea which I have given to you. Now let us go through the sequence of steps which will be involved for this purpose. Now as the stack pointer is pointing to the top of the stack, any data cannot be loaded there because it will be having a data already loaded onto the stack. So we have to first decrement the stack. So the stack pointer will be first decremented by 2. So stack pointer equals to stack pointer minus 2. After that, once the space has been created onto the stack, the flag register will move onto the stack. So the content of the flag register, or I can write content of flag register, this will move on to the stack. Now the top of the stack is pointing to the content of the flag register, that to the lower byte. After that, the microprocessor will check the status of your interrupt flag, and if the interrupt is allowed, what the microprocessor will do is it will make your interrupt flag as 0 and your trap flag as 0. The purpose of doing this is this will disable all your maskable and single step interrupts. Now why is this done so? Since the microprocessor is now already in the process of executing an interrupt service routine for the interrupt, it would not like to get disturbed by another interrupt which is a maskable in nature. So in order to disable it, it has made the interrupt flag as 0. It has disabled the single step interrupt by making the trap flag as 0. Try recollecting that the priority order of your single step interrupt was the least one. So that is why it has disabled the single step interrupt also. In the fourth step, it will decrement your stack pointer again so that it can load another set of values. So this stack pointer will be decremented by 2, and then your code segment, that is the current code segment which is of the next instruction for the program which it was executing. So the code segment value, code segment, this moves on to the stack. Now I would like to highlight here the code segment. Here is the code segment is of the next instruction of the ongoing program. So this is the program which the microprocessor was executing, and in between it has got interrupted. So this is the address of the next instruction. Then now the stack has got filled up again, and the top of the stack is pointed by the stack pointer, and it is pointing to the code segment value. After that, the stack pointer will be decremented again. So I can write stack pointer equals to stack pointer minus 2. So I can create a space here also, stack pointer minus 2, and then the content of your instruction pointer will be loaded. So the content of your instruction pointer will also move to the stack. So as like in the fifth step, the instruction pointer is also pointing to the next instruction of the ongoing program. So these two needs to be saved so that once the ISR is executed, so the code segment and the instruction pointer value from the stack is popped to their respective registers, and it will start, or it will resume from the next instruction. After that, what will happen is the code segment and the instruction pointer are loaded with new addresses derived from the interrupt type number. So this we have already seen how it is derived. So it will see which is the type number of the interrupt which has been encountered, and depending upon that it will calculate physical address from the value 4n and 4n plus 2, and it will obtain the CS and IP values, and they are loaded accordingly. So CS and IP values, once they are loaded, the microprocessor will be able to calculate its physical address, and then it will jump to that location for executing the ISR. So the ninth step will be the 8086 microprocessor executes the ISR, or in some cases, or in some text it is written as ISS, interrupt service subroutine. So both the things mean same, interrupt service routine to service the interrupt. Now once this is done, after this is the basic steps which are involved in servicing an interrupt. So after these 9 steps are done and the interrupt has been serviced, the microprocessor needs to go back to from where it has left. So it will go to this ongoing program. So how it will go, it will pop out the respective contents. So first what it will pop out, if you have followed these steps, you will understand that here the instruction pointer will be popped out first, then your code segment will be popped out, and finally your flag register will be popped out, because your stack works on the principle of first in last out, or last in first out. So with this we are done with your 8086 interrupts, and we have covered all the topics. In the next video we'll be moving to our next unit, that is unit number 7, which is your interfacing chips. If you have any doubts in this unit, you can either comment in the respective videos, or you are free to even mail me.